Good morning, students. It gives me great pleasure to talk to students through video presentations like this as usual. This particular video presentation, you can call it as derivatives part 2. Now here let me take an example. If f, g are derivable, by the meaning of derivable I mean to say that f dash of x is equal to limit h tends to 0 of f of x plus h minus differentiable derivable. Differentiable you can even say is existing. That's the meaning of existing. Here again you can, as in the case of continuity, I can even call it as left hand derivative. Left hand derivative is limit h tends to 0 of f of x plus h minus f of x whole by h. Okay, right hand derivative, okay, is equal to limit, this is h minus 0 minus h tends to 0 plus of f of x plus h minus f of x whole by h. Or at a particular point a, let us say this is a, this is again a, this is a, this is a. This is left hand derivative at x equal to a. This is right hand derivative x equal to a. If left hand derivative, right hand derivative, they both exist, they both are equal, then only I mean to say it is differentiable at the point x equal to a. Instead of x, I put a particular value a. I mean to say I should have the left hand derivative, right hand derivative, both should exist, both should be equal. Both should be equal. That's the meaning of function to be differentiable at a particular point. Okay, both left hand derivative, right hand derivative should exist and should be equal, and that is the particular what value I am going to get. It's the corresponding derivative at that point. That's the corresponding derivative at that point. Okay, now listen, show that, just listen carefully. Show that y is equal to f of x equal to mod x is not differentiable, differentiable at x equal to 0. It's not differentiable x equal to 0, I should say. Okay, now you know very well mod x is x if x greater than or equal to 0, minus x if x less than 0. Of course, everybody knows. Now listen carefully. Let me think about left hand derivative. This is limit h tends to 0 minus of f of 0 plus h minus f of 0 whole by h. It should be f of 0. Okay, f of 0 whole by h. This is by definition of left hand derivative. This is limit h tends to 0 minus of, this is f of h. F of 0 is anyway 0 divided by h. H tends to 0 minus means it's a value below 0. For any value below 0, it is minus h by h. Therefore, this is limit h tends to 0 minus of minus 1, which is equal to minus 1. Now, right hand derivative, of course, at x equal to 0, I should write at x equal to 0. I mean to say limit h tends to 0 plus f of 0 plus h minus f of 0 whole by h, which is equal to limit h tends to 0 plus of f of h minus 0 by h. H tends to 0 plus means it's a quantity above 0. Therefore, it is h minus 0 by h, which is equal to limit h tends to 0 plus of 1. Therefore, left hand derivative is minus 1. Right hand derivative is plus 1 at x equal to 0. Therefore, LHD not equal to RHD implies y is equal to f of x equal to mod x is not differentiable at x equal to 0. Let me repeat the whole process. Let me think about LHD at x equal to 0. Limit h tends 0 minus f of 0 plus h minus f of 0 by h. I already told you limit h tends 0 minus f of a plus h minus f of a by h is the left hand derivative x equal to a. Instead of a, I have 0 here. Now this is reduced to f of h minus 0, but h tends 0 minus means it's a quantity below 0. It's reduced to minus h by h is minus 1. Similarly here f of h is plus h by h is 1. Therefore left hand derivative is minus 1, right hand derivative is plus 1. Therefore left hand derivative not equal to right hand derivative. Therefore the function is not differentiable at x equal to 0. Function is not differentiable at x equal to 0. Are you able to follow clearly? Is it clear for you? Is it clear? Okay. There is one more standard theorem. Show that every differentiable function is continuous. Every differentiable function is continuous. Okay, let y is equal to f of x be differentiable at x equal to a. A is an arbitrary real number. Let us just say it's an arbitrary real number. Okay, just let us say. Now, what does it imply? Limit h tends to 0 of f of a plus h minus f of a whole by h is a finite quantity. This quantity is finite. That's the meaning. This limit should exist. Or you can even say f dash of a is equal to this much. It's a finite quantity. Let me just start with limit x tends to a of f of x. This will be is equal to limit, what do I get? H tends to 0 of f of a plus h I get. Okay, this is taking x is equal to a plus h. Okay, now what I will do here is I'll just add f of a, subtract f of a and add f of a. Okay, now I'll apply limit for this separately. A plus h minus f of a whole by h into h plus limit h to 0 of f of a. Now this is a finite quantity. You just seen into 0 plus this is f of a is equal to 0 plus f of a is equal to f of a. Now for limit x tends to f of x, f of a implies f of x is continuous at x equal to a. Therefore, I mean to say every differentiable function is continuous. Let me take y equal to f of x be differentiable at x equal to a for a real number a. Therefore, this limit is a finite point. This real meaning of function to be differentiable at a particular point. Now, let me start with limit x tends to f of x. Limit h tends to 0 f of a plus h taking x equal to a plus h. When x tends to a, h tends to 0. I'll subtract f of a and add f of a. I'll apply limits for this individually and I'll multiply and divide by h over here. I'll again apply limit for this separately. This limit becomes 0. This limit is a finite quantity. This becomes 0 only when 0 multiplied with a finite quantity becomes always 0. That's the real meaning of assuming this to be differentiable. Therefore, I come to the conclusion. It becomes continuous at x equal to a. A being arbitrary real number, it's going to be true for any such case, any real number for that case. Therefore, every differentiable function becomes continuous. Every differentiable function is continuous. Let me just take the application of this easily. Okay, easier case. Show that y is equal to f of x equal to box x is not differentiable at x equal to 2, let us say. Okay, just listen carefully. What I will do here is I will do an easy method over here. Now LHL at x equal to 2 is equal to limit x tends to 2 minus box x, which is limit x tends to 2 minus, for any value below 2, box value is 1. This is reduced to 1. Okay, this is reduced to 1. Next, RHL at x equal to 2 is equal to limit x tends to 2 plus box x. For any value above 2, box value is 2. Therefore, LHL is equal to 1. RHL is equal to 2. LHL not equal to RHL. Therefore, limit x tends to box x does not exist. Implies y is equal to f of x equal to box x is discontinuous at x equal to 2. It implies y is equal to f of x equal to box x is not differentiable at x equal to 2. It not differentiable at x equal to 2. Because only in the previous theorem I told you every differentiable function is continuous. If it is differentiable, it has to be definitely continuous at a point. I have proved it is continuous at a point. Therefore, it can't be differentiable. If it is differentiable, it becomes automatically continuous at a point. I am able to prove it is discontinuous at every integral values. 2 is an integer. Therefore, it can't be differentiable at the point x equal to 2. It can't be differentiable at x equal to 2. It cannot be differentiable at x equal to 2. Okay, I can think about the function to be differentiable at x equal to 2. Okay, if f, g are differentiable, show that f plus g is also differentiable. F plus g dash of x is equal to f dash of x plus g dash of x is also differentiable, and show that this much. Answer, let me think about the answer now. Okay, just listen. Limit h tends to 0 of f plus g of x plus h minus f plus g of x whole by h. What I will do is, I will write f of x plus h minus f of x whole by h separately, plus limit h to 0 of g of x plus h minus g of x whole by h separately. This is nothing but f dash of x plus this is nothing but g dash of x. Now for f plus g dash of x now becomes, this is f plus g dash of x anyway. Okay, let me repeat. Limit h to 0 of f plus g of x plus h minus f plus g of x by h. Limit h to 0 of f of x plus h minus f of x by h. I'll group these two and group these two separately. I'll put plus sign in between. This is f dash of x, this is g dash of x. Therefore, differentiation of sum of two functions is the sum of the individual derivatives. Similar way, I can apply for subtraction also. F minus g whole dash of x is nothing but f dash of x minus g dash of x. Okay, next one more result. Just think about f, g are continuous functions. F, g are continuous functions. Show that, okay, f, g whole dash of x is f of x into g dash of x plus g of x into f dash of x. This is called product rule of differentiation. This rule is called product rule of differentiation. Let me think about the final answer. Let me call this as okay, anyway, f g whole dash of x is equal to limit h tends to 0 of f g of x plus h minus f g of x whole by h, which is equal to limit h tends to 0 of f of x plus h into g of x plus h. What I will do is, I will subtract and add g of x. Okay, f of x, g of x into, this is f of x into g of x whole by h. Just listen carefully. I'll just subtract and add f of x plus h into g of x. Sorry, I'll subtract and add f of x plus h into g of x. I need it, therefore I do. Now what I will do is, I'll write f of x plus h into g of x plus h minus f of x plus h into g of x whole by h plus limit h to 0 of f of x plus h g of x minus f of x into g of x whole by h, which is equal to limit h to 0 of f of x plus h into limit h to 0 of g of x plus h minus g of x whole by h plus limit h to 0 of, I'll write g of x separately, into limit h to 0 of f of x plus h minus f of x whole by h. Therefore, due to the continuous nature of the function, this is reduced to f of x into g dash of x plus g of x into f dash of x. That is first function derivative second plus second function derivative first. That is known as derivative of product of two functions. Therefore, this is called product formula. Okay, now I repeat, f g whole dash of x fg whole dash of x, okay, is equal to limit h and 0 fg of x plus s minus fg of x. That is f of x plus s and g of x plus s. I'll subtract and add f of x plus s into g of x. Okay, let me apply limit for this separately, for this separately. Let me take f of x plus s common, apply limit for this separately, limit for this separately. This is g dash of x. They both are continuous and differentiable. Mention the differentiability also. Then only this I can write this g dash of x. Here it is g of x into f dash of x. Okay. Due to continuous nature of f, I will replace h by 0 over here. Why not we think about why should I consider both to be continuous? Because I can add and subtract f of g into g of x plus s also. There I will be using limit h and 0 of g of x plus s equal to g of x. That's the reason why I am calling both to be continuous. Both are continuous as well as differentiable. This is called product rule of differentiation. This is called product rule of differentiation. Okay, this rule is called product rule of differentiation. Okay, next, let f, g be two continuous functions, continuous, in fact differentiable function. Okay, then d by dx of f by g of x is equal to g of x into f dash of x minus f of x into g dash of x whole by g of x the whole square. This is called division rule or quotient rule. Division rule or quotient rule of differentiation. Quotient rule of differentiation. Quotient rule of differentiation. Okay, just listen. Now f by g dash of x is equal to limit h tends to 0 of f by g of x plus h minus f by g of x whole by h. Just listen. What I will do is limit h tends to 0 of f of x plus h by g of x plus h minus f of x whole by g of x whole divided by h. Let me just take LCM. What do I get? F of x plus h g of x minus g of x plus h f of x whole divided by g of x plus h into g of x into h. Okay, now let me just let me continue here, which is equal to limit h tends to 0 of f of x plus h g of x. Let me just subtract f of x into g of x and add f of x into g of x minus g of x plus h into f of x divided by g of x plus h into g of x into h. Now let me apply limit individually as in the previous case. What I will do here is I'll take g of x as common into divided by, I'll get it to be g of x plus h into g of x into limit h tends to 0 of f of x plus h minus f of x whole by h. In fact, let me take minus as common here. I get it to be limit h tends to 0 of, I will just take f of x as common by g of x plus h into g of x into limit h tends to 0 of g of x plus h minus g of x whole by h. Therefore, this is reduced to g of x into f dash of x by g of x the whole square plus this is f of x into g dash of x, minus, there is a minus sign in the middle, minus g of x the whole square. Therefore, since g of x is a common denominator, I can subtract the numerator. Therefore, this is reduced to g of x into f dash of x minus f of x and g dash of x by g of x the whole square. You can even call this as denominator into derivative numerator minus numerator into derivative denominator whole divided by square of denominator. Let me repeat, f by g whole dash of x is limit h tends 0 of f by g of x plus h minus f by g of x whole by h. This is f of x plus h by g of x plus h minus f of x by g of x. I have taken LCM, f of x plus g of x minus g of x plus f of x by this much. Subtract f of x g of x and add f of x g of x. Here take g of x is common, write limit for this separately. Take limit for this becomes f dash of x. Now take minus as common, apply limit for this separately, limit f of x by this much separately and this separately. This becomes z dash of x. Therefore, g of x and f dash of x minus f of x and z dash of x by g of x the whole square will be the final answer. G of x whole square is a common denominator. You can even call it as denominator and derivative numerator minus numerator and derivative denominator. Whole divided by square of denominator. Square of denominator. That's how it goes. That is how it goes. Okay. Now we have just seen composition of functions. Okay. We have just seen composition of functions already. Okay, if f, g are continuous differentiable function, then f composite g dash of x is equal to f dash of g of x into g dash of x. This rule is called chain rule of differentiation. Okay, let me get the answer here. F composite g whole dash of x is limit h tends to 0 of f composite g of x plus h minus f composite g of x whole by h, which is equal to limit h tends to 0 of f of g of x plus h minus f of g of x divided by, I will write this as g of x plus h minus g of x, multiply and divide by this, into g of x plus h minus g of x. Apply limit for this separately. I can write this h tends to 0 as g of x plus h tends to g of x. Since it is continuous, I can write like this. This is nothing but f dash of g of x into this is g dash of x. Let me repeat. F composite g whole dash of x. This limit h tends to 0 f composite g of x plus h minus f composite g of x whole by h. This is f of g of x plus h minus f of g of x. What I will do here is I will multiply and divide g of x plus h minus g of x. I need it, therefore I do. This particular limit automatically becomes z dash of x. Since g is a continuous function, when h tends 0, g of x plus h minus g of x tends to 0. I can write the denominator tending to 0. G of x plus h minus g of x tending to 0. Therefore, this limit becomes automatically f dash of g of x, okay, into g dash of x. This rule is called chain rule of differentiation. This rule is called this chain rule of differentiation. Okay, let me just take one example in each. Okay, if y is equal to sin x into cos x, find dy by dx. What do I get? This is product rule, sin x into d by dx of cos x in plus cos x into d by dx of sin x. Okay, therefore this is sin x into minus sin x plus cos x into cos x. This is minus sin square x plus cos square x. Therefore, this is reduced to cos square x minus sin square x, which is also equal to cos 2x. This is by product rule of differentiation. Let me repeat. Dy by dx is sin x into d by dx of cos x plus first function derivative second plus second function derivative first. Sin x into minus sin x plus cos x into cos x. Therefore, cos square x minus sin square x. This is the application of product rule of differentiation. Okay, let me just think about division rule. If y is equal to sin x divided by cos x, dy by dx becomes cos x into, let me just check, this is nothing but tan x. Let me just check whether I am able to get secant square x using your division rule. Cos x into d by dx of sin x minus sin x into d by dx of cos x whole divided by cos square x. Therefore, this is reduced to cos x into cos x minus sin x into minus sin x whole divided by cos square x. This is 1 by cos square x, which is secant square x. Therefore, derivative tan x is secant square x, everybody knows. I write it as sin x by cos x and I am applying chain rule. Therefore, I mean to say it is nothing but cos square x plus sin square x is 1. After applying division rule of derivatives, it gets reduced to automatically secant square x. Just listen carefully. Listen carefully. Here you mean to say y is equal to sine 2x. I call it as y is equal to sine u, where u is equal to 2x. Therefore, how do I get the solution here? dy by dx is dy by du into du by dx. This is called chain rule. What is derivative of sine u with respect to u? Cos u. What is derivative u with respect to x? Which is 2, sorry. Therefore, this is reduced to 2 cos 2x. If you want to do it directly, derivative of sine 2x is cos 2x into derivative 2x is 2. That's the meaning of chain rule. I repeat, sine u where u is 2x. Therefore, this is written as dy by du into du by dx by chain rule of differentiation. By chain rule of differentiation, proof of which I gave you just now. Chain rule of differentiation. Therefore, it gets reduced to cos u into 2. Therefore, 2 cos 2x is the final answer. 2 cos 2x is the final answer. Therefore, due to time constraints, let me stop here. I'll continue in the next video. Thank you students for patient watching.